Hello, everyone. Can you all hear me? Okay na, sir? Should we start na? So, sige.
Yeah, I can hear you.
Okay, sige. So, right, guys. So, welcome to the fourth Quantum Computing Natural Language Processing lecture series. So, there's a quick change. So, before, back then, it's just the Javis and the team. But right now, I'm the one hosting for today. So, I am Sean Balayas. I'm the chairperson of affairs over at Dev8. So Dev8 is a local developer community based here in Eastern Visayas. And right now, I'll be your host for today. Okay, sir. So next slide po. So just remember, just like during the past sessions, past series, make sure you engage yourself actively and you immerse yourself in this wonderful session. Hi, Sean. So make sure it's going to be open. Make sure that you're open to each other. Let's have a really wonderful conversation. This is an intellectual affair, so make sure it's gonna be fun. And if you have any questions, don't be shy. But if you're still shy, feel free to send those questions to me, and I'll try to relay them to one of our speakers. And lastly, let's respect everyone. Okay. So next slide, po. So before we start, we'd love to ask, how are you feeling today, po? Two. Okay, so Daryl here says, oh, Katenza says here she's ano. Okay. So that's a lot of twos, a lot of threes. So it seems like everyone had a really tiring week, no? Two, sige. Ooh, there's a lot of twos. Okay, guys, try to hang on there. Life has its own challenges, and hopefully we can all tackle them successfully. And good luck, huh? Thank you for joining, even if you're tired. Thank you for spending time, spending this weekend in learning more about quantum computing, particularly on quantum natural languages. And I'm happy to see the very familiar names joining us. Hi, Vaughn. Right. So there's a lot of twos. So are you all excited na for today's sessions? Even just type yes or no. That'll be fine. Are you ready? Or do you want like nice breaker? But anyways, it seems like everyone's ready. So see you next slide, po. So for the first session for today, we'll be talking more about basic programming in Python, and the speaker for this session will be Jedediah Ramos. He's a quantum research fellow over at QCSP, and I'd love to give the Zoom to Mr. Ramos to introduce himself.
All right, can you hear me?
Yeah, Jedediah, is that you?
Yes, that's me.
Yeah, we can hear you.
All right, so I'm Jedediah Ramos. You can just call me Jed. That's Jed. So my topic will be about basic Python programming. I'll share my screen soon. Right, can you see this now?
Yeah, we can see it. Jed.
All right. So here's a super quick introduction to Python programming. So after these slides, I'm actually going to show you some actual Python programming in Colab or Jupyter Notebook. So I'll try to go over these slides quickly so that I can show you the more immersive experience of actually coding. So first off, here's the coverage. We're going to be covering very basic Python syntax and very basic data types like strings, numbers, arrays, lists, and tuples, and basic control structures, your usual conditional statements and loops, how to define functions, And we won't need to cover advanced features like lambda functions and input output and regular expressions like that. And no external libraries like NumPy, Pandas, and SciPy. And so here we go. So firstly, what is Python? Let me try to move this. So Python was created by Guido van Rossum, and it's a high-level language. So usually know about those low-level languages. The very first one would be assembly. That's the computer language itself. And then you can go up like C and those higher ones. And then Python is right near the top. It's very easy to use. So it's easy to read and write, and it very closely resembles human language. And this makes it an excellent language for beginners. It's an interpreted language as well. There are compilers and interpreters. And so the compilers are more efficient, for example, at catching syntax bugs or things like that early on. Interpreted languages are convenient for executing your code line by line, which makes debugging easier. And it's dynamically typed. You don't need to declare the data type of a variable explicitly. So you'll be talking about things called variables. These are containers to hold data or your information. And there are different types of information. It could be strings like text or numbers as decimal points. And in other languages, you would actually have to declare what type of data you're using. But for Python, you don't have to do that. That's what's so convenient about it. And so the Python interpreter infers that data type during runtime. So it's also open source. Python is freely available and can be distributed and modified. And it's run by a large community of contributors. And so first we have variables. It's a container, like I said, that holds data, and it's a way to store information. And you can use that and manipulate that information at any time throughout your program. And so we have a bunch of naming rules that you would need to remember. Although this is a thing that you would be very familiar with if you're already an experienced programmer. So these can include letters, numbers, and underscores. So for example, here we have something called my variable, and then it must start with a letter or underscore. So variable names like var1 or var or underscore var2. And then it cannot start with a number like this one var. That's not acceptable. And it's also case sensitive. So for example, my var, and my var, all of them sound the same and are the same words, but the spelling are different. And you can actually declare these variables in the same program, and your program will recognize these as different variables just because of the spelling. And next, avoid using Python reserved words. For example, if, else, class, for, and things like that. And then that means reserved words as names of your variables alone. But you can actually mix reserved words, like for example, if var or else var or things like that, so long as it's not exactly the same as the reserved word. And then you can assign values, like the equal sign to assign values to variable names. For example, my age equals 15 and student name equals Alice. And for things like text, you would need quotes to signify that that's text. Next, we talk about data types. So Python has several built-in data types, and here are some of the most common ones. So first we have integers or int. These are whole numbers. They can be positive or negative or even zero. An example is age equals 16. And they're floating point numbers. So there can actually be floats or doubles. Although in Python, you don't have to specify. These are numbers with a decimal point. For example, height is 5.9, presumably feet, or you can even make your format in meters or anything like that. And the operations are addition, subtraction, multiplication, division, floor division, exponentiation, and modulus. So addition and subtraction and multiplication use your typical symbols like the plus and minus, multiplication with the asterisk symbol, and division with the forward slash. And floor division has the double forward slash. And the difference between those two is division can actually work with decimal points. So for example, if you do 1/2, that would be 0.5. But if you do 1/2, that would be 0 because it doesn't care about the remainder. It just preserves the integer data type of that. And then exponentiation is just double asterisk. For example, 2 asterisk 3 would be equal to 8. And then modulus is just division, but not getting the quotient. It gets the remainder of your division operation. And next we have strings. And it's a sequence of characters. It can include letters, numbers, and symbols. And it's enclosed in quotes, like mentioned before, like hello, Python, and even triple quotes. So it can be single quotes or even double quotes or triple quotes. And you can actually do operations in strings like concatenation with the plus sign, repetition with the multiply sign. So it's like you're multiplying the string, and then there's slicing and indexing. And then the methods for operating on strings as well are dot upper, and then lower, replace, split, and so on and so forth. And then we have Boolean data structures. These are very basic data structures in information science and computer science as well. So these represent logical values that can be true or false. And these are exactly the things that are used in conditional statements. And then we have lists, which are an ordered collection of items, and lists are changeable. So you enclose these in square brackets. Example is a list we call fruits, and the contents of that list are apple, banana, and cherry, just for example. And then you can operate a list as well. Like you can access what is the first element of the list, what is the second element of the list. That's what accessing is. Then you can modify. You can specify which elements to change or which to add or remove. That's append or remove. And then array and matrix as well. An array is a special case of a list where the elements have the same type. And so normally in a list, you can have different types. Maybe some of these can be strings in the list and some can be integers and some can probably be floats. But as for the array, all of the elements in the list have to be of the same type of data. So either all strings or all integers or something like that. Usually it's integers or floats. And it's usually numeric and is used in computations. So this is an example of an array. It's declared is in pretty much the exact same way as a list. And it can be represented as a list of as well, where each inner list represents a row. So just like this, you see here that there are lists inside the list. So it's a list of size 3 containing 3 lists of each with its own size of 3. And so next we have tuples. These are similar to lists. They are also ordered, but they are immutable. They cannot be changed. And you enclose these with parentheses. So you can use these to signify things like coordinates, like shown here. And next we have dictionaries, which are an unordered collection of key value pairs. So the way you define these is you label each content of the dictionary. For example, the name is Alice, and you separate those actually with a colon, and then the grade is 10. That's just an example. And similar operations here, like access, modify, add, and remove. And a dictionary is also known as a hash table. That's a slightly advanced concept in programming. So you don't need to be very familiar with that for these purposes. And so these are examples of a dictionary. So let's move on from that. Next we have you can actually check more information about dictionaries. There are all sorts about them. Next we have sets, the typical one from set theory. These are an unordered collection of unique elements. So you enclose these in curly braces, but with no key value pairs, unlike the dictionary. So for example, we have for colors, red, blue, and green. And then there is no indexing or slicing here, and no duplicates allowed. So for example, we have a list, or rather a set, that contains the elements red and blue. And then we have another set that contain red, red, and blue. Those two sets are actually the same set because in the other set, we duplicated red, but sets don't care about duplication. So those are sets are only defined by membership, and that's why they are actually the same set. And so you use a set when you need to ensure elements are unique, and you're primarily concerned with membership testing, or you need to perform set operations like unions and intersections. And so here's an example of a set. Instead of your square brackets for lists, you use curly braces, like in this example with my set, and then you can print the set there. And you can do slicing as well. You can slice a string or an array or a list in Python. And this is to extract a substring of that original list or array or string using a start index and an optional end index. So here are some examples. So here we have the typical string hello world. It has several letters. I believe that's 11 if I'm counting correctly. And then if we slice from 2 to 5, that gives you the letters LLO. That's because we start from index 1. You have to recall in programming you start with index 1. So rather not index 1 but index 0. So that's the common thing in programming. So at index 0, the letter is H. And then letter number 1 would be E. Letter number 2 would be L. And that's why it gives you LLO. And we stop at letter number 4 at 0, 1, 2, 3, 0, 1, 4. So that gives you letters from 2 to 4 because we stop right before the last index. And then we can even emit the world from that by using S and then bracket colon 6. And then that only prints hello without the world because we're ignoring the rest of it. And we can even get the substring starting from index 2. And we specify that with 2 and then colon. So once again, it gives us LLO plus world. And we can even get the last 3 digits, and we use the negative this time. So -3 gives us the last digits, RLD from world. And then we can even print every second character using colon colon 2. And then you can reverse the string, colon colon -1. And then you can get characters from the third to the last, to the second last. So -3, -1 gives you RL because the third last element is R and the second last is L. So in general, slicing is applicable to sequences, an ordered collection of objects where each element can be identified by a unique index, where the index starts from 0. So another interesting topic in Python is something called list comprehension. So list comprehension is a concise and efficient way to create lists in Python. So more readable and expressive syntax for creating a new list by applying an operation to each item in an existing sequence and optionally filtering elements based on a condition. So these are like for loops, but using them to initiate or initialize lists. So this is the general syntax. So you enclose it in square brackets for lists, and then you do the expression for the item and sequence if condition, or something similar to that. I'm going to show you more list comprehension later. And these are some examples for now. You can have, for example, x equals you. So the name of your list is x. And then the condition is I for I in range 0 to 4. So that gives you a list of numbers from 0 to 3 because we stop right before index 4. And then you can even do all even numbers between 0 and 9. And the way we did this here is using modulo 2. So if it's even, then we include that in the list. 0 to 468. And even modular exponentiation. This is relevant here because of quantum algorithms like Shor's algorithm and other cryptographic protocols that rely on modular exponentiation. But for now, we won't be talking about that. Anyway, let's look at type conversion. there's implicit conversion, which Python automatically converts one data type to another, and explicit conversion, manually converting one data type to another, such as int, float, string, and so on and so forth. Then we have control structures. So these are your if statements and for loops. So these actually control the flow of your program. And these are exactly the things that are powerful in programming. These are absolutely essential things, and you'll see why soon. And the if statement is used to execute a block underneath it. And that is signified with indentation in Python. And it executes only if you have to supply a condition to it. And if the condition is true, then the statement becomes executed. Otherwise, it does not execute the statement and skips it. And so here's an example. We set x to 10, and if x is more than 5, then we print the string below. And this will really print the string because the condition is true, because 10 really is more than 5. And then we also have elif, which is else if, and else clauses can be added to create more flex. So that actually allows for more conditions. So we can check for multiple cases other than just one case. And I'll show you more of that later. And you can use a for loop for iterating over a sequence. So you can use these to probe your data structures like lists and sets and things like that. So for each fruit in your list of fruits, you can print each of those elements. And then these for loops in Python are flexible because they can use the range function, like for I and range, rather than the syntax you see here for fruit and fruits. And this is an example here for I and range 3 that actually prints the numbers 0, 1, 2 because we stop right before that last index, number 3. And then there's also the while loop to execute blocks of code repeatedly. And here's an example. So instead of using the for I in range, we can do that manually ourselves, that like you can see here. But we have to increment that counter inside the while loop by ourselves. So that really prints 0, 1, 2 like earlier. But with the complication here that we had to do that more manually than for I in range. And then we have error handling as well, using try and except. So here, we're trying to set a result to 10 divided by 0. And then if it fails, we can instead print division by 0 is not allowed. And that's because math leaves division by 0 undefined. And so this actually allows us, using the try statement, if it fails, then we can resort to the except statement right there. And that actually prevents your program from clashing, from crashing. And then we can also use finally blocks for the try except to once again account for more conditions. And then we have functions as well. These are blocks of code that you can define and then reuse over and over again. Like for example, def greet name. So def means to define. And then the name of the function is greet. And here it takes an input. As you can see here, the input is called name. And then it's used to greet whatever your name is or whatever name you input. And then you can call these functions at any time. Like for example, here we greet Alice and we have to input the name that we want to greet. And that is the output. So functions can also return values using the return keyword. So here's an example. We have a function to do addition on elements, and it returns a plus b. So instead of printing, it just returns a value. And we have to make sure to catch that value. So we can print afterwards, or we can define another variable to contain whatever the result is. And here's an example of that. The result is whatever the sum is, and you can print the result. So here's an example of returning multiple values. You can return the sum, and you can return the difference, and other kinds of results that you want to include. And then you can unpack return values into separate variables. And then you can also import modules. So in Python, the import statement is used to bring in modules which are simply Python files. So these actually allow you to import all kinds of packages or modules. And you can access functions, classes, and variables defined in other files. So you can use this to access other files and promote code reuse and modular programming. So these are bite-sized pieces that you can reuse. And then here's some basic syntax of the import statement. So you have to import and then whatever the name of your module is that you want to import. And you can also make specific um names for these, like from the module, you import the specific part of the module. That's also allowed. And then if you do from module import and then asterisk, this imports all the public contents from that, although it's generally discouraged because it can lead to conflicts with similarly named items in the current namespace. If you happen to have variables or things like that that have similar names to the module that you're importing. So for example, we import math, and the math module can do all sorts of things like square roots and more. And so lastly, that's the end of it, or almost, because lastly we have to ask why Python. The reason is because you can because it's the universal language of many um current most recent technologies and programming and quantum computing as well as machine learning. So you have things like Qiskit and Ocean and scikit-learn, Keras, and TensorFlow. So it really is a universal language in the computing and the quantum computing industry, as well as machine learning and artificial intelligence. Many of these, if not all of these, use the same language, which is Python. And that's why you have the biggest incentive to really learn Python, because it's like your one-way ticket to everywhere and and many more, not just these specific technologies that I've mentioned here. And so from that, I'm going to share another screen. Right, can you see this screen now? All right, thank you. So this right here that you see is called Google Colab. So, or it's also called Jupyter Notebook. And so these are this allows you to code in Python online on your browser. So it uses Python. So we can try a bunch of exercises here to demonstrate. So exercise one, create variables of different types, for example. So here we can assign an integer to a variable named age. So let's say age equals, let's say 25 or something like that. And then assign a float to variable average score. Let's say 5.2. And then favorite color. And as you can see here, I don't have to specify what types of data I'm using. That because the Python program can guess what type of data it is based on the number or string that I input. And then favorite color, I can, for example, say red. And then I can print each of these and print their type using type. So for example, I can print age. And then when you run this, it has to connect because it has to allocate runtime to connect to Python 3 Compute Engine backend to run this Python code. So that takes a bit of time, but only usually a few seconds. And that is only pretty much a one-time thing for every session. So as you can see here, it prints number 25 because that's the age that I specified. I can also print the type of the age. And that naturally is going to print something like int. Now let's try the others, which are average score, and then the type of average score. And yes, it prints class float, which is 5.2. So you get the idea. And then next we have string manipulation. So let's create a string, we just call it var, with the value Python is fine. And then we can print the length of that using the len keyword. So first of all, let's try printing the string. It prints exactly the string that I specified, or we can print the length of it using len, and then the length of the variable. It just counts how many characters there are, and there are 14 characters in the sentence, including the exclamation point. And then we can print the first three letters of this var. For example, 3. And it indeed gets us the first three letters, PYT, for Python. And then next we can try basic arithmetic, create two integer variables and perform. So let's say var1 is, let's say 2, and then var2 equals 3. Actually, let's say 3 and 5. And then we can try printing the results of these, like for example, var1 plus var2. That gives us naturally 8. And then we can also try the others, even this negative numbers, var2, -2. And then we can even get, let's try the others, var1 times var2, right? 1 divided by var2. Let's say, for example, var2 modulo var1. And so for the regular division, it prints 0.6. But then for the floor division, it prints 0. And let's try to see that by reversing the operation or reversing the operands. Then here it prints 1 because when we divide 5 by 3 and ignore the remainder, the quotient is just 1. And then 5 modulo 3 is 2 because that's the remainder of dividing 5 by 3. We can also do exponentiation. For example, print, let's say, for example, var1, var2. And that gives us supposedly 3 to the power of 5. Let's try smaller numbers. 3. So 2 to the power of 3 is 8. And another thing here says use exponentiation to build a very large number. So I'd like to show you something very interesting about Python, which you will not see in many other languages. So as you can see, it prints this ridiculously large number. And if you try to do this in languages like C or C++, C Sharp, or if I'm not mistaken, or Java, the your integer data type is just usually 32 bits. And if you try to print this, that's going to overflow because your 32-bit integer is not going to be able to contain this number. And we can even keep going. I'm just going to add zeros to the power, and it's going to print a very large number. But actually, it has a limit. It exceeds the limit 4,300. So it seems you can go as much as you want, but that's not necessarily the case. And then it actually can fill this whole line on the screen. So let's look at the next parts. Create a list. Let's say a list for one. Let's just call it fruits, actually. 5 different fruits. Apple, banana. And you can have the choice to put spaces in between your items, or you don't need to do that. Say, Actually, let's just do chair and orange. And we can print this whole list, roots. And here's something interesting. You can actually put a comma at the end of your list, and that's still going to be valid. And you can actually print the first element of your list. Let's say fruits. So that's index 0, and that's going to print apple. And when you put index 1, that's going to print banana. And then you can also try index -1. That gives you the last element of this list, which is orange. And so let's try adding a new fruit to the list. So another interesting thing about Google Colab or Jupyter Notebook is that about Jupyter Notebook is that even though we specified one code part here, we can actually continue that in this next section here in modifying lists. For example, we can still access fruits that we had earlier. We can append a new fruit, like for example, what can we append? Like for example, strawberry. And then we can print the new list. And now it has 6 fruits in it instead of 5. Then we can also remove something from it. Like for example, banana. And then we can print the result. And now it only has these elements in it. So these are the elements of the list minus banana. And so let's look at the next one, which is list operations. Create a list of 3 numbers. So nums. And then let's say 3, 5, and 8, or 81, for example. Let's just do something modest like 359. And then we can print the sum of these numbers. So we can actually do that using an operator called sum. And that's going to print the sum of the list. 3 plus 5, forgot to print. And it's going to print the sum of the list. Sure enough, the sum is 17. Or we can even print the average, which is the sum. Actually, let's define average, which is the sum divided by how many elements you have. And then we can print the average. And that's the average. And then we have different ways to make lists, which is another interesting topic in Python. So we can, for example, create a list using multiplication. So let's say mul list equals 0 times, let's say 5, and we print. And that gives you a list of 5 zeros because we actually initialized a list of just the element 0 and then 5 of those. That's what we mean by multiplication. And then it could actually be any element you want, not just 0. And then we can also do list comprehension like we mentioned earlier. So list comprehension, for example, 0 for x in range, let's say 3. That's going to be 0, 1, 2. So forgot to print. Never forget to print, guys. And so this gives us a list of 3 zeros. Let's try something else, or another one, which is using a for loop. So what do we mean by that? So let's try an empty list. So empty list equals, let's say this. And first of all, let's try printing the empty list. And that's going to give us just empty brackets. But another thing we can do is for I in range using a for loop, let's say 5, we append to the empty list dot append, let's say 7. And then that's gonna give us 5 sevens because we manually added 7 to the list 5 times. And so that's another way to initialize a list. And if you try to compare these, um, the slowest one is obviously the for loop, and then um list comprehension and multiplication actually come close. In some cases, the multiplication can be faster, but then there are different reasons for why you should not use multiplication, especially when you're doing lists inside lists. You'll see that soon here in nested lists. So you can create a 2D matrix. So 2D equals, for example, and then naturally this is going to give us a matrix, although it just prints it in one line. If you don't like that format, another thing you can try is print every row in the list, like so. And then it's going to print them separately in multiple lines, like that. And then next, let's try making a 3D matrix. So, and that's going to be even more complicated because you have to put lists inside lists 3 times. So let's say 5. And you really have to carefully keep track of this. If I'm not mistaken, this supposed to uh, and here it gives us 3 entire layers of nested lists. And then here's the last thing we can try. We can create a list and then insert lists inside that list. So for example, we have or actually let's just try to replace the 0. And then if we print the lists, what we get is just that ordinary list. But then another thing we can try is setting index 2 of that to be another list, like this, for example, and then print the new lists. And supposedly now you see that index 2 is replaced with this list inside the list. And you can keep doing that. You can even put another list inside that, and it's going to work as well. Just like that. And you can keep doing that in theory infinitely many times if you had that much power. Then there are different ways as well to make nested lists. You can use list comprehension as well. So for example, do D plus, and then you have to do 2 sets of brackets. Actually, let's say 2, 4, Y. So it's just like 2 nested lists and two nested for loops. And then we can print that. Although better to just print each row in that list. And then just like that, we have a 5 by 5 array or matrix of the same element using the list comprehension. And then another important thing I would like to show you is using multiplication. So equals, for example, 3, and then times 5, and then times 5 again. And then we'll see the result of that in, in Actually, I should put space between them. And here's something interesting because we can print, or rather we can replace indices. So by the way, the way to access indices in these nested lists is using two layers of these brackets, like 3 and then 4 equals, let's say, 10. And then we can print this again for row in D rank row. And then as you can see, we've changed an element here in 10. Like we've replaced a 2 with a 10. But what happens when we try to do the same thing with the list multiplication? Let's say mult, and then let's say 2, 3 equals, let's replace it with a 7, for example. And then we'll print everything again. And as you can see, it changed the whole column up with 7. We only wanted to change one index, one single cell, and yet the whole column was changed. And that's because it allocates the same like memory. Like these are actually the same copies of the same list. So these are all the these are all copies of the same row. And so when we change an element in one row, something changes in every other row. And that's why for nested lists, you don't want to use multiplication. So let's move on from that. We have tuples and sets. So so for example, we have colors like red, blue, and then green. And we can print that tuple, and that gives us exactly that. And unlike lists, you cannot modify the tuple. So for example, we change red to, for example, um black, and then we print the colors again, and it's going to forbid that. We get an error message because we are not allowed to change the tuple because tuples are immutable or unchangeable. Next, we have sets. But by the way, we can still print each element of the tuple. For example, we can print colors. If I'm not mistaken, this should give us red. And exactly, it gives us red. So next we have sets. Create a set of 5 different numbers. So nums. So and then we can add a new number to that. Append, let's say 11, and then we remove 5 from the set. And then we can print the numbers again. And now we have the new set with 11 but without 5. Oh wait, sorry. It's supposed to be with brackets, with curly braces. And it's not append this time, but it's add. So these are the sets. And then we can actually check if there's an element or member in that set. So for example, print um 11 in nums. And supposedly that gives us true because 11 really is in that set now. But then if we try to print 5, as we recall, we removed 5, so it will give us false because it's no longer in that set. So next, let's try creating dictionaries. So for example, we have student, Then the name of that student, let's say, would be Alice. And then the age of that student would be, let's say, 16. And then their grade, let's say, 10. And then the way we access these is student. Then we can print the name. For example, we have to specify it with a string. And supposedly this is going to give us Alice. And then we can print the student's age, specified also with a string. And that supposedly gives us 16. And then we can modify dictionaries as well. And like we said, we can access it again here. We can change, or rather we can add a new key value pair, for example, favorite subject equals, let's say, math. And then we can even change things in the dictionary, like the grade. It used to be 10. Let's say it's now 11. And then let's try printing the student. And as you can see, the grade is now 11, and we've already added a new key value pair, which is the favorite subject, which we defined as math. And then um we can also delete parts of it like del student and then age. And the age value will no longer be in here. So we only have name, grade, and favorite subject. And then we have data type conversion. I'm just going to copy paste this here just to breeze through. And that supposedly gives us so we, as you can see, we've converted between data types. So num str used to be a string called 42. And then we can convert that to an integer first and then increment by 1. So that's why we got 43. And then we can get the integer from that and then convert that back to a string because of this str num int. And then we can work with user input. So if I'm not mistaken, um, let's say x equals input, and then we can print that input. Let's say +1, just so we know we're doing this right. And the way it works is I have to input something like, let's say 5, enter, because it accepts strings. So let's say we concatenate instead. Let's say input it. Let's say hello. And then that concatenates the string. And another thing we can do is conditional statements. So if two numbers are the same, print same. So let's say num1 is 5, num2 equals 7. And then if if num1 equals num2, we print same. And this is not going to print same because they are different numbers. But if we set both of them to be the same, then it gives us same. And then we can even directly put that inside the condition itself, and it gives us the same result. And then we have else statements as well. So compare two different numbers and print the smaller one. So num1 equals 5. And then if num1 is less than num2, print num1. Then we say else, we print num2. And this supposedly gives us whatever is smaller. And indeed, 5 is smaller. And then we have elif statements to account for more conditions. To compare first number to the second number and print less than, equal to, or greater than. So let's say num1, let's just say n1. equals 4, and 2 equals 5. And then if n1 is less than n2, then less than L, and then we say elif n1 equals n2, we print equal, else we print greater than. So those are the only possibilities. And then here it's less than. And then when we set them to be the same, it's equal. And then here we will have greater than. And then next we have while loops. Set the variable to 5. Then increment it by 3 until it exceeds 20. So while x is less than 20, we increment this using the plus equals operator. And then by 3. And then let's say we print the x inside the loop. And then this gives us every iteration of the loop until it exceeds or until it gets to 20. And if we do, we can change the increment amount and it takes a different path. And we can, one thing we can do is also put the print before that so we don't see the 21 because it's not supposed to exceed the 20. Then for loops, print numbers from 1 to 10. So for I in range 1 and 10. Although we'll see the problem with this because it's not going to print 10. So 1 signifies the starting position, and then 10 is the last index. But it doesn't print 10 because it has to stop right before that. And that's why we have to specify 11 instead. And that gives us 1 to 10. Then nested for loops, print numbers from, and another thing, by the way, is we can also specify a third one, which is how much to increment by. So that gives us 13579 because it skips by 2. We can also skip by 3 every time using 11, 3, 1, 4, 7, 10. We have nested for loops. So print numbers from 1 to 25 in a 5 by 5 square grid. So the num, let's say, is 1 or 0. And then for I in range, actually, let's say for x in range, say 5. And then for y in range, 5. And then here we print, although before that we have to increment by 1. And then we can actually avoid going to the next line by specifying that this must be NP, or we can do tabs. And then here we can go to the next line. And supposedly this is going to give us 1, 2, 3, 4, 5. But oh, we're not supposed to print X, we're supposed to print the number. And now it gives us a grid of 1 to 25 using this nested for loops. And then here's the almost the last one. We define functions. So we can define a function to add two numbers and then return the sum. We use the def keyword and then sum, or let's just say add. Although actually we can't, there are some, let's just say sum two numbers. So A and then B. And then return A plus B. Then what we can do is print, and then we can call that function inside this. Actually, better yet, we can define it in a variable equals sum of two numbers. And then let's say the two numbers are 5 and 7. And then we can print the result. And we expect to have a sum of 12. And there it is. Then we can also have return values. So we can also add as well as multiply. So sum and product. Let's say A and B again. And then we can return A plus B as well as A times B. That gives us two return values. And then let's say um the sum, and we have to separate them with a comma actually, and the product equals sum and product. Let's say 3 and 5, and then we can print the sum, and then we can also print the product. We expect 8 and 15, although we can actually print that in a single statement, sum and product of 3 and 5. That print that gives us a tuple because that's actually what the return values are. And here we have lastly no return values. So we define a function and call a function that prints the input is and then prints the input. And then we also try that with a list where we pass a list without returning the list. So for example, def A, then we print the input is and then A. And then we can call that with, for example, hello. And here we have the input is hello. And then we can also try making a list. Let's just say nums equals, let's say 3, 5, 7. And then let me define the function first. Okay. Modify. And then let's say it just modifies the first element of the list. So nums 0 equals, let's say 1. And then modify nums. And we print nums. And so you have to be careful sometimes with your functions because here there's nothing stopping us from putting anything that is not a list as an input. And that's going to ruin the program. So as you can see earlier, we have 357, but now we have 157 because we modified that inside our function. And that means we can use a function to take in a list and then modify it from inside without giving back the list because it's taking a reference, it's not passing by value. Whereas if we were to, for example, def modify num a, or let's say this time b, let's say b is now incremented by, let's say 5. And then let's say we define something called c equals 10. And then we modify that number, or at least we'll attempt to do that here. And then we print c. And that is not going to give us 15, it's going to give us 10. Because unlike the list, it does not get a reference to that number. It gets the value. And so that's what we call passing by value and not passing by reference. And there are others here that you can perhaps try by yourself. So I won't go over those here. So this should be the conclusion now of my presentation on demonstration on how to code in Python. So thank you for watching and listening.
All right. So, okay, can I be heard? All right. So, thank you,
Yes,
Jed.
Ken.
Okay, thanks. So, thank you, Jed. That was a really wonderful presentation. Before we continue, do we have any questions from the ano? Oh yeah, Jed, Carlo is asking if you're going to share the collab link.
Well,
Jed.
I suppose I can share it later.
Mhm.
I'm going to ask Sir Bobby and the others first
Okay.
about this.
Alright, actually, that was a really nice presentation. It really got the basics. Like you really got the basics hammered down. And actually, I've been using Python for over around 11 years now at this point. So I'm just gonna ask this for the sake of curiosity, no. And siguro some people are wondering, are there any cases when Python would not be the ideal solution for a quantum computing related problem?
So for quantum computing related question, if if you've asked the question in in a general context, I would
Yeah.
have said the answer is definitely yes, because I've
Mhm.
tried making my own experimenting programs to run things by brute force. If you
Mhm.
run it in C or C++ or Java, it's very fast.
Yeah.
But if you run it in Python, it's very, very slow. But for quantum computing applications, I haven't heard yet about specialized I wouldn't be surprised if there are specialized languages to run faster for those.
Mhm.
Although there are faster alternatives in Python, like you can use NumPy
Mhm.
to quickly. Although Carl here in the comments says that there are frameworks that use C++ under the
Oh
hood
yeah.
for quantum context. So
Okay.
fortunately, you have other options.
Okay, yeah, that's good. Even actually NumPy is actually C under the hood. They just have Python bindings that we use. So,
Uh, to add to that, there is
ah,
also
Sir Bobby say speaking. Hi,
yeah,
Sir Bobby.
there's also a framework from Microsoft.
Mhm.
It's using it's called Q Sharp, but it's actually C Sharp. So if you like C Sharp, then you can try Q Sharp.
Ah, the Q language. Yeah, yeah. It's the
Yeah.
new, it's a recent language. I think, di ba, Sir Bobby, at least around
No.
2016?
Uh, uh, you mean the
Q
C
sharp.
Sharp?
Yeah, the Q sharp.
I was already exploring Q Sharps. So ano pa lang 2017 pero di kasi gumana sa Mac during that time kaya nag-Python na lang.
I think since Microsoft is already supporting is having more support for cross platform technologies, even their latest .NET framework is more or less cross platform. Siguro no, it could already be run in the Mac.
I think hindi ko na lang na-try.
Hmm. All right, so we have a question from an anonymous participant. Uh, they ask, for developers, are you creating your own modules for quantum computing? That's the question.
Okay, you can create your own modules based on, for example, Qiskit. Um, if you have a new algorithm or yeah that you want to distribute to other people, then you can create a module in Python and just reference it from Qiskit. Yeah,
Okay,
that's it.
so Mr. or Miss, I don't know, I don't, did that participant, did that answer your question, or do you have any follow-up, Boba? Okay, Carlo is asking, are there specialized packages being used in quantum computing?
Yes, the packages that are used in quantum computing are usually specialized. Like for example, the the Q sharp is a DSL of .NET, and the and also there are a lot of Python-based quantum computing frameworks that are available. Qiskit is just one of them. The other one is Google search, no? So although Google search is actually the learning curve is quite steep, no? So yung so for beginners, usually we just use Qiskit. It's very straightforward. Yeah, I hope that answers the question.
Okay, so let's have two last questions. So let's have it from Edwin and the anonymous participant for the sake of time. Okay. So first, let's go with Edwin's question. So Edwin asked, how do classical Python algorithms compare to quantum algorithms in terms of complexity?
Yeah, I think Carl
Carl just
answered.
answered it. Yeah.
Let me see. Let me just read Carl's answer. That depends. So the question is, how do classical Python algorithms compare to quantum algorithms in terms of complexity? So the answer of Carl here is that depends on the type of the problem you're tackling. For certain problems, quantum algorithms that give an advantage, and for others, it gives an exponential speed up. Yeah, so to add to that, no, nandito naman kayo, di ba, nung last week when Dr. Henry Adorna gave a talk on complexity. Yeah, so may mga classical algorithms that na mas I mean may mga algorithms that cannot be that are just hard to to reproduce that are hard to quantify, no? Kumbaga, create a quantum alternative. So usually uh, yung mga algorithms na to, like for example, yung mga algorithms like sa operating system na nakikita natin, di ba? Or algorithms that are used to update the graphics of your screen, di ba? Or algorithms that you use in order to build the Microsoft Excel or Word, no? Those are things that you don't want to hindi kaya yan ng quantum computer. Kasi quantum computer is not designed for those things, no? Yung a good example is arithmetic, di ba? When you add 1 plus 1, alam mo kaagad that's 2, di ba? Pero sa quantum computer kasi, it will give you a different answer every time you run it, no? Pero because it's probabilistic, it means that if you run it example 1,000 times, mabilis naman kasi yung yung quantum computer. So run 1,000 times, in every run you get an answer. Like for example, 2.1, no? Tapos run ka na naman, it will give you 1.9. And then you just get all of the results, and then you do a expectation, or what you call this, a expectation value, or the average, no? Now the average of that is 2. Now, would you rather do classical or quantum for that kind of problem, no? So yun yung so classical ang gagamitin mo dyan. Pero there are just problems also that quantum computer is really very very fast, no, in terms of computation, no. Like for example, yung alam to ni Edwin kasi si Edwin is from Bulacan State University. Yung tawag nito, yung di ba yung ginagamit nating encryption ngayon, which is dalawa lang naman yung sikat dyan eh, no? It's the RSA and the elliptic curve, no? Now, ito kasing RSA and elliptic curve, both of them have the same, ano, problem structure, no? They are both instances of what is known as the hidden subgroup problem. Na itong hidden subgroup problem, sobrang galing mag-solve ng quantum computer nito, no? So, ang classical computer, kaya niya mga for 2048 bit na hindi naman impossible, no? Pero it is estimated to be 300 trillion years, no, bago ma-crack yung yung ano, yung RSA encryption of 2048 bit. No? Kaya we are very safe kasi no one no one here can probably live up to 200 years, di ba? Much more. 300 trillion years, no, which is more than the age of the galaxy, no? The age of the galaxy is in the order of billions lang naman, no? So, magaling yung quantum computer to solve those kind of problems. And yung classical algorithm, classical algorithm, yung complexity niya for that problem, no? For that problem, kasi ano yan eh, that's parang sequential search yan eh. It's on the average, 2 to the 48 is, on the average is 2 to the 1, 1024, no? It's still a very large problem, very large number, no? So, pero yung quantum computer using Shor's algorithm, na let us say, assume that we have already a fault-tolerant quantum computer that can run Shor's algorithm, mabilis lang yan because yung complexity niyan is just the logarithm of 2 raised to the 2048, no? Or actually, ano yan eh, 3 times log of n, no? So, ano yan siya, it's exponential, no? So, ganun yung ano niya, yung complexity ng quantum computer compared sa yung ano, which is 2 to the n, sobrang laki, no? Yan.
All right. So thank you, Sir Bobby. There's one super last question. So they're asking, is it advisable to run Qiskit locally, or is Colab already enough?
Oh yeah, but for only very small qubits, no? Kasi na-try ko na yan for 10 qubits. Naghang yung naghang yung laptop ko. So, you can probably try dun sa Colab. Meron naman silang ano eh, GPU. Yeah, you just have to pay
Yeah,
for it.
there's a GPU there.
Oo.
Like, Nvidia,
Uh,
Nvidia, I forgot. Yeah, sige.
yeah, NVIDIA.
So super last, super last. We're
Sige, sige.
gonna close the questions for the sake of time. Can quantum computers, quantum algorithms now do parallel programming or sequential pa lang?
Oh, that's a very good question, no? Yung, I think merong ano yan eh, merong initiative to use distributed quantum computation, no? So which is of course the same as parallel computing now, pero quantum. Pero yung quantum computing itself is also ano din siya, it's called microparallelism, no? Parallel computing in the small. The only difference is that the only difference between a supercomputer that does parallel computation and the quantum computer that does parallel computation is that sa quantum computer kasi when you, for example, run for example, you want to crack the RSA, no? Meron kasing subroutine dyan called the modular exponentiation, no? So itong modular exponentiation na to, it will compute the modular exponent, no? Or ng ano ng for all possible values of 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 your input, no? So diyan pumapasok yung Hadamard's, no? So for example, meron kang 3 qubits, then if you apply a Hadamard to that, then all possible values of the 3 qubits are the following, no? 0, 1, 2, 3, 4, 5, 6, 7. Now, if if you uh, pass this, into a quantum modular exponentiation subroutine, what the quantum computer will do is compute in parallel yung mga sagot na yun, no? Yung mga modular exponentiation of uh, each individual number. Pero the thing is, it can on it will only do that as long as you're not observing, no? So it will compute as long as you're not observing. Now, if you want to get the answer, you will have to observe. Ang tawag dyan, measurement. Ang problema lang is that if you measure, it will only give you one answer, no? So ngayon, ang tanong is if everything is equally likely to be given, no? A probability of every one of them is the same, then every time you measure, you get a different answer, no? So on the average, all of them will have the same probability of occurring. Kaya nandito na pumapasok yung creativity ng mga tao, no? And it's so hard, no? Kasi until now, dalawa lang talaga yung algorithm that is really very creative, very important, no? At ito yung tinatawag na Grover's algorithm, which is the algorithm you use to search an unstructured database, and the other one is the Shor's algorithm, no? Now, bakit ko nasabi na you have to be very creative? Kasi for you to tell the quantum computer to give me the correct answer, you will have to program your gates in such a way that it will the probability of the correct answer the probability na makukuha mo yung correct answer is very high compared sa probability of the other answers. So ganun yung challenge ng quantum algorithms, no? How do you create quantum algorithms that do that, no? Kasi every time you measure, isa lang binibigay sa'yo na answer, eh. No? Out of the 2 to the 48 and possible answers, ay bibigay sa isa lang. Diba? Now you have to assemble your quantum gates. Quantum gates are your computation, no? In such a way that yung correct answer, a probability of it to be measured is very high. So ganon siya. So iba siya sa parallel programming talaga na alam natin.
All right. So thank you, Sir Bobby, for answering those questions. So thank you, everyone, for those wonderful questions, no? And I think we learned a lot. So let's move on now to the next slide. So before we move on, kumusta man ka mo? Kumusta? How are you feeling right now? We need to do this temperature check. There's a lot of topics, lot of terms being thrown around. Okay, that's good. Good. We're five. I'm seeing fives. Okay, good. That's good. Four. Oh, okay, that's okay, Vaughn. There's a three. Ooh, there's a three. Yeah. Okay, those are really good signs. Five. Okay, that's a lot of fives. A lot of fives. 5 plus 1. Oh, 6. Is that 5 plus 1 gonna overflow to 1 ba? Just kidding. Okay, that's not to 4, that's to 5. All right. Okay, that's really good. Okay, now let's move on. Next slide po, Sir Bobby. Oh, okay. So, let's do a 5-minute break, sir.
Yeah, 5 na lang.
Okay. So, sige, start na lang the timer, sir. Move pa natin.
Yan, hindi ko alam
10
pa.
pa lang. Tapos, i-move na lang natin to 5. Forward pa, sir. Forward. Sige pa. Sige pa, sir. Ah,
Yan.
yun. Yes, tapos yung beat natin, sir, para... Yeah, I think okay naman.
Mute na.
Yeah. Next time, sir, sa next one? Yung upbeat, sir, para
Sorry.
okay lang, sir. Alright. So, see you guys in a few minutes. Let's take a break. Let's take a breather. So, yun. Alright. Welcome back, everyone. So, is everyone alright? Dito na ba lahat? If you're here, type 1 or type 2. If you're here, 1. 1, alright. Okay, so everyone, 2. Alright, so everyone's here. Okay, welcome back, everyone. So we're gonna go now to the second session of our lecture series today. So for this next session, we're gonna have Sir Bobby Corpus Jr. And today he'll be talking more about quantum concepts and block sphere. So I would like to bring the floor to Sir Bobby. Sir Bobby?
Salamat. So I will just share my screen. Yan, share ko muna to. Then I will share in the other device screen. Broadcast. Okay. Okay. So yeah. So good afternoon. Good evening. Yung yung topic natin ngayon medyo siya medyo theoretical. And the reason for that is because we wanted you to understand the foundations of quantum computing. On a high level kasi, you can do quantum computing naman without understanding these concepts. Although hindi siya ideal, no? Kasi you would not know kung bakit talaga gumagana tong quantum computing, and why do we bakit natin siya gagamitin, no? Hindi lang dahil mabilis siya on some problems, but we also want to know paano gumagana yung quantum computing na yan, no? So, because it's a probabilistic, alam naman natin na quantum computers are probabilistic, no? Which means that whenever you get the answer, it gives you different answer every time, no? Pero paano siya gumagana, no? Pero let's begin with with let's begin with the basics muna. And ang unahin natin is, di ba alam natin na yung quantum computing na mention to ni Elmer last time, no? I just have to ask a feedback siguro. Sean, is my voice clear naman? Kasi I'm not using a headset, eh. Oh, okay, sige. Salamat. So, na-mention ni Elmer na a quantum computer is quantum computing is using complex numbers, no? And yung complex numbers na yan, it turns out na it's actually integral, no? To the theory of to quantum theory. Meron kasing ibang mga mathematical techniques, no, that are used that uses complex numbers para mapabilis mapadali yung mga computation, mga derivation, no? And at the end of the computation, they just throw the complex part, and then they get the real part, no? Yun yung sagot, no? Pero yung quantum computing is intrinsic sa kanya yung complex numbers, no? So ito yung mga sinabi ko kanina, no? So the complex numbers are as real as can be, no? But we know that quantum theory is the theory of reality, no? So if the theory of reality needs complex numbers in order to describe reality, then complex numbers are not imaginary. No? They are as real as can be. So let me show you yung isang what you call this experiments of physics, no? So this one is called a Mach-Zehnder interferometer, no? So ang ginagawa nito is maglagay ka ng isang laser dito. So may laser dyan. Tapos you fire the laser on a beam splitter, no? So the beam splitter is meron siyang half silvered siya, no? So 50%, there's a probability 50% na a photon will be reflected, and the other one naman, so 50% probability that another photon will be transmitted, no? Now pagdating dito sa full silvered mirror, because it's full silvered, ibig sabihin reflect talaga yung reflect yung beam, no? And then it will hit another mirror here, which is a half silvered mirror, and my probability that the photon will be transmitted or reflected. Tapos meron tayong dalawang detectors, no? Detector D1 and detector D2. Tapos we are going to measure ano yung intensity ng photons each detector. Now you can describe this using quantum theory, no? Okay, so imagine that you have a yung state ng photons mo is this one here, psi, no? Tapos yung psi na yan, this is equal to yung state niya, no? Yung state niya is dalawa yung pwedeng mangyari sa kanya, no? It can be transmitted or reflected, no? So you can describe the state of the photons hitting the beam splitter to be equal to the probability A that it will be transmitted plus the probability B that it will be reflected. Now, pagdating niya sa full mirror, dito sa full mirror, no? It will be reflected at yung kanyang state magiging G, no? Magiging G. At pagdating naman dito sa ano na to, banda dito, yung kanyang ma-reflect din siya at yung state magiging H, no? So itong G na to, it will hit the beam splitter dito. And either magiging matransmit siya at yung kanyang ano, yung kanyang state is maging ganito, no? So let me just write the state, no? Yung state G is the probability that it will be reflected, no? Reflected B. Oh, sorry. Yeah, B. Tapos, kasi, sorry. Kasi reflected siya, no? The probability that it will be reflected, ibig sabihin, itong L na to, no? Kasi L is reflected, no? L. Tapos meron din siya probability that it will be transmitted, which is yung K na to, K. Okay? So, plus the probability that it will be transmitted. Now, itong H naman, no? Itong H, we can also compute for the state of H, no? So, kapag ma-reflect siya, ibig sabihin K, no? So, the probability of being reflected B, tapos K. And the probability that it will be transmitted, A, tapos yung state na transmitted siya is itong L na to, no? Okay. So, ibig sabihin, yung sign natin will now become, kasi yung sign natin is the state, no, of the system, no? So, yung state of the system can now be written as, itong state na to, it can now be written as A, H, kasi di ba kanina, pagdating niya dito, naging H and G siya, di ba? So, AH, H is the probability of transmission, di ba? And since na-reflect siya, R, di ba? R, pag na-reflect, no? So, ibig sabihin, sorry, so G pala, G. So, G. Okay, so I'm talking about this one here. Yeah, so this one and this one, H and G. Okay, now, itong H and G natin, ito yun eh. Ito yung inano natin. Yan yung ating kinumpute kanina. Therefore, if we substitute that to psi, it will give you A, tapos yung H mo is ito, no? So BK plus AL. Okay? Tapos plus, sorry, may kulang ako dito, no? This is B. B, tapos yung G mo is BL plus AK. Okay? Now ngayon, if we simplify this, no? If we do the multiplication, simplify to 2A 2AB K is the state, plus A squared plus L. Okay. Okay, that's as mathematics is concerned, no? Ito yung theory. Now, the experiment, what does the experiment tell us? Now, the experiment tell us that none of the photons are detected in D2. Okay? Wala dyan, no? Lahat ng photons nandito sa detector 1. No? So, ibig sabihin, kapag wala sa D2, ang ibig sabihin yan, itong state na L na yan does not exist, no? Or in other words, zero yung kanyang probability. Zero, no? Of occurring. Pero ito kasing A and B na yan, those are probabilities of being reflected and transmitted. So, ibig sabihin, ang value niyan is not zero. In fact, yung value niyan is 0.5, no? There's 0.5 probability of being transmitted and 0.5 probability of being reflected. So, if that's the case, and quantum theory is correct, then A squared plus B squared equals 0. How can we make sense of that, no? So, it turns out that, sorry, it turns out that A squared plus B squared is equal to 0 if A is equal to IB, no? Where I is your imaginary number. So that is the reason why complex numbers are very much intrinsic talaga, no, sa quantum theory. Kaya imaginary numbers are not really that imaginary, no. They are used in describing physical reality, and the physical reality is described by quantum theory. Okay, so that's the trivia, no? Oh, sorry. Okay. So actually, I just skipped all of this because I was just explaining. Now, dito na tayo sa review of mathematics na. Because this one is a medyo theoretical siya na, there will be some elementary mathematics na, hindi naman totally elementary, but things that you already know, no? Because you already are in, alam niyo na to, you have covered this already in your calculus siguro, no? Some of these concepts, and some also in high school. So, review of relevant mathematics. Ito, napaka-simple lang nito, no? Triangle, no? So, if you have a right triangle, and one of the angles is theta, then the opposite of that, B, is equal to R sine theta, no? Kasi yung R natin is your hypotenuse, no? And also the side A, no? Hindi yung band, side A is equal to R cosine theta. Okay. So far, so good. Now, trigonometric identities. So ito, gagamitin din natin ito mamaya, no? So this is the trigonometric identity of sum and difference of two angles now. Okay, so for example, if itong, so alam, so these are quite familiar, no? So gagamitin natin yan mamaya. Okay. Now, spherical coordinates. So gagamitin natin itong spherical coordinates mamaya in order to discuss the black sphere, no? Now, if you have a point in three-dimensional space, like this one here, this point here, then it can be described by not only the Cartesian coordinates x, y, z, but also spherical coordinates r, theta, and phi, no? So yung theta natin is the elevation, no? The angle of elevation or polar angle. Tapos yung r is the distance of the point from the origin. Tapos is the azimuth, no? Okay. Now, ito yung kanilang transformation, no? So, I think we already this one is familiar to you na, no? Tama ba? This one is familiar to everyone. So I can skip this. Okay. So that's the spherical coordinates. So naman, Taylor expansion, no? So kailangan natin itong Taylor expansion because alam naman natin na yung quantum computing gumagamit ng mga exponential of complex numbers, no? So, or a complex number can be written as an exponential. Kaya, kailangan natin yung expansion ng exponential, no? Oh, ganun pala. Okay, so ito yung exponential of x. Tapos, we also need the Taylor expansion of sine of x and cosine of x, no? So, ganun siya. Okay, no? So, tingnan nyo lang yan, no? Sa later, magagamit natin. Okay. Next is the bracket vectors. I just want to do some review. Pero na-mention na to ni Elmer dati, no? So, ang ket vector is the vector that is ano yung ginagamit natin in order to describe a quantum state, no? So ito yung kanyang itsura. Okay? So meron siyang what do you call that? From greater than sign. So it's called a ket vector, no? And yung nag-invent ng ano na yan, ng symbol na yan or ng notation na to is si Paul Adrian Maurice Dirac, no? He's one of the inventors of quantum mechanics, no? And his book on quantum mechanics is the best book I have read so far, no? So Paul Adrian Maurice Dirac. Although after reading that book, wala kasi siya mga exercises, so you would not know if you have learned anything. So you cannot apply it to any problem. Ngayon, the inner product. So if you have two vectors A and B, then the inner product is symbolized as this one, no? So kapag may makita kayong ganyang symbol, ibig sabihin, that's the inner product. So the inner product is a complex number. Okay. Now, if you are a mathematician, itong A na to is actually a linear functional, no? Which it's a vector that lives in a separate vector space called the dual space, no? But we're not going to talk about that here, no? So it's suffice to say that this notation is what is known as the inner product. Now ngayon, kapag ini-swap mo, no, you swap the order Instead of AB, ginawa mong BA, no? So, ang mangyayari dyan is, if you swap the order, then you will have to take the complex conjugate, no? So kapag ini-swap mo yung order, you take the complex conjugate, then you get the original ano, value, no? Now, itong quantity na to, you might be surprised to see that quantity, no? I'm not sure if na-discuss to ni Elmer. So this is actually a operator, no? It's called a projection operator. Tapos ang ginagawa niya is, remember yung mga dot product natin? If you have a vector A,
Battery is 100%.
and then you dot it to vector B, then the geometric interpretation of that is, it is a yung A dot B is the component of A along the direction of B, di ba? So ganun yung projection operator, no? So it projects a vector B along A, no? So here's an example, no? So itong example na to, no? Itong operator na to, we apply it to B, and then ito yung magiging itsura niya, no? So pinagtagpi mo lang itong dalawa. Pero ito, this is already a complex number, no? Which is called the, what do you call it? The inner product. So the inner product multiplied by the vector A. So ibig sabihin, it's a, the projection operator projects your vector B into the direction of A multiplied by the component of B along A. Okay, so that's the, so ano na-discuss natin dito? This, the inner product and the projection operator. Okay. Now, suppose you have a square matrix. Yung square matrix mo, if you operate it on A or apply it on a vector A, but then you still get the same direction of A, but probably contracted, no, or or elongated. So ibig sabihin yan, yung matrix mo is ganito, no? So yung factor na to na lambda, which stretches your vector A, or not only stretch, no, or probably contracts, no, but since this is a complex number, no, we can just probably say it stretches or elongates, no, along the direction A. So lambda is called the eigenvalue, and A is called the eigenvector of the operator A. Okay, so what do you call this? Ini-interchange ko na lang yung operator and matrix, no? Pero actually, yung operator is general, no? It's called coordinate free, no? Ibig sabihin, it's a quantity that exists on its own, independent of any coordinate system, no? So it's more general, no? But when you want to do quantum computing, usually you pick a basis, no? Itong basis na to, which is 0 and 1, no? It will give you the matrix, no? Of your operator. Kaya minsan interchange ko na lang yung words. Kasi yung canonical basis, yun ang palagi natin ginagamit, no? Which is yung 0 and 1. Now, suppose you have this thing here, and you want to get the complex conjugate. Ano magiging itsura niya, no? So magiging itsura niya is yung lambda mo, which is a complex number, you take the complex conjugate of that, no? And then yung vector mo na A or ket mo, magiging bra na siya, no? Magiging bra. So ganitong magiging itsura niya, no? Magiging bra. Now, if there is no ambiguity, no, what you can do is just put this inside, no? Ang ibig sabihin yan, multiply the matrix representation of the vector A by lambda star, no? Or lambda, or the complex conjugate of lambda. Tapos, remember that the matrix representation of your this one is a bra vector, is a row vector. Row vector siya. So, ibig sabihin, ganyan itsura niya, no? Hindi ganyan. Okay? Ito kasi yung ket, eh. Tapos ito yung bra. Okay. Okay, now, paano kapag may operator ka that is applied to a ket? How do you get the complex conjugate? So ito yung itsura niya. Ganyan, no? So, yung matrix representation ng A, you get the complex conjugate, and then, nabaliktad yung order. Kasi ito, this one is a column vector. Sorry, this one is a row vector na. Ito is column. Ito is a row, no? Tapos nabaliktad, no? Nabaliktad yung representation niya. Okay, so that's a review of mathematics. Now, dito na tayo sa Bloch sphere, no? Which is the actual topic. Okay. Now, the ket A, the ket psi, no? Psi, yeah, suppose the ket psi is the state of your qubit, no? So, qubit natin is isa lang, no? Isa lang. And it is and it's represented by this linear combination of 0 and 1. Tapos, A and B are complex numbers, no? So, if you remember, A and B are what you call them? The probability amplitudes, no? Probability amplitudes. So you can represent any state of a qubit in terms of the superposition of its basis vectors, no? Weighted, kumbaga yung weights niya is the A and B complex numbers. Now, since A and B are complex numbers, you can write A and B like this, no? So, x sub A plus I, y sub A, no? And the same goes for B. And you can conveniently represent it also as a exponential, no? Ito, where RA is the magnitude of your complex number, no? Magnitude of your complex number at e to the I phi A, no? So this one is the complex form, the polar form, the complex number, no? Now, therefore, we can write psi as this one here, no? So, ang A natin, ginawa lang natin ganyan yung A. And yung B natin, ginawa lang natin ganyan, no? Okay. Now, alam naman natin na, I'm not sure if you remember, but the state of a quantum system will not be affected if you multiply it with a global phase factor, no? Kasi if you multiply it with the global phase factor and you measure it, the global phase factor will just cancel itself out, no? It will just cancel itself out. So ibig sabihin, it cannot be observed. Now, we are going to use that trick, no? Ang gagawin natin, we are going to multiply this by a global phase factor because we want to derive something, no? So we multiply it with a global phase factor. And anong global phase factor are we going to use, no? So we are going to use the complex conjugate of this global phase of that exponential, no? So which is this one here. Para pag multiply mo, it will cancel at yung matitira na lang is RA. Tapos, if you multiply it with this one here, ito yung magiging itsura niya. Okay? And then if you convert it back into rectangular coordinates, kasi alam naman natin na this one is also a complex number, no? This one is a polar form, then we can always convert it back into a rectangular form. So RA 0 na siya plus X plus IY, no? Plus times the state 1. Okay. So nilagay ko lang yan dito. Okay. So ito siya. Now, because alam natin na by normalization, we always normalize, no? Our quantum states, no? By the normalization condition, alam natin na how do you compute for the no? For the norm, no? Ang gagawin mo is you square this and you multiply this with its complex conjugate, no? So if you multiply x plus iy to its complex conjugate, you will get x squared plus y squared, no? Tapos ito, RA squared is equal to 1 by the normalization condition. So, and then we are going to relabel RA, no? Para lang for aesthetic purposes, gawin natin siyang Z, no? No, kapag ginawa natin siyang Z, ano yung makikita nyo? What you'll see is nothing but the equation of a sphere, no? So x squared plus y squared plus x squared plus y squared plus z squared is equal to r squared, no? In this case, r squared is equal to 1, okay? So r squared is equal to 1, meaning r is equal to 1, no? Now, but ibig sabihin, this is the equation of a sphere, di ba? So ibig sabihin, we can now describe our qubit in terms of spherical coordinates, no? Kasi it's very natural, no? It's very natural na because of the normalization condition, nakikita mo yung equation of the sphere, no? So it's easier to use spherical coordinates rather than the Cartesian or rectangular coordinates. Okay, pero alam natin na in spherical coordinates, this is true, no? Alam natin yan, no? X, Y, Z in terms of r, theta, and phi. So what does this mean? So kapag ginamit natin yan dito, and knowing that this one is Z, no? RA is Z, then ito yung magiging itsura niya. Ganyan. Okay, now you factor out sine theta. Okay, factor this out. So ang matitira is cosine theta plus cosine phi plus I sine phi, no? Okay, pero alam natin that this one is nothing but e to the I phi. Okay, so kaya this is the general form of a qubit, no? nakita nyo na tong nakita nyo na tong equation na to eh. Ginamit to ni Elmer. Pinakita niya sa inyo, no? Pero this is how that was derived, no? This is how that was derived. Okay. So that's the qubit, no? So already described using spherical coordinates, no? Okay. Now, pero alam naman natin na in the what do you call this? In the spherical coordinates, itong ating theta, ito yung theta, di ba? Itong ating theta goes from 0 up to 90 degrees, no? To 90 degrees. So ito yung 90 degrees, di ba? Pero kasi alam natin na pero gusto natin kasi na kung hanggang 90 degrees lang siya, ibig sabihin hemisphere lang siya, no? Hindi siya hindi siya sphere. Hemisphere lang. So anong gagawin natin in order to for it to be for all points on the sphere to describe your qubit, no? To describe the states of your qubit, no? Ano yung gagawin natin? So ang gagawin natin is we introduce a variable. Okay? So phi prime, theta prime is equal to 2 theta. So by doing that, we can now rewrite this one here. So ito na yung general state ng qubit. No? Ito yung pinakita ni Elmer sa inyo, no? So ganun siya. And the sphere that describes that visually is called the Bloch sphere, no? Bloch sphere siya, no? So ito yung state mo. So ibig sabihin yung any point on that sphere describes the possible state of a single qubit. So there are infinitely many possible states, no? Now, if you compare this with classical computing, there are only two states, no? 0 and 1. Pero dito, it's an infinite number of possible states. Okay. So that's the Bloch sphere. Now, physical interpretation of an operator. So, I think na-mention na dati ni Elmer na meron tayong quantum gates, di ba? So, meron tayong quantum gates. And these quantum gates are operators, no? And operators are represented by matrices, no? Okay. Okay. Pero I try to just operate on this level as much as possible, no? If hindi na talaga kailangan, then I will, kung hindi na talaga pwede, I will introduce the coordinates, no? Or the matrix representation. So operators medyo abstract na yan, no? So itong so for example, what's the operator X? When you operate it when you apply it to the qubit 0, it will flip this into qubit 1. Tapos, in the same way, the reverse is ito yung magiging itsura niya. So that's the X gate, no? Or the NOT gate, no? NOT. NOT gate. No? Now, what's another operator that we can use, no? The Hadamard, no? The Hadamard operator. If you operate this on 0, it will give you this. Now the square root of 2 there is because we normalize the state, no? So if you normalize the state, then meron kang factor na 1 over square root of 2. And if you apply this on the state 1, it will give you 0 minus 1 over square root of 2. Anyway, what am I trying to say here? What I'm trying to say here is that itong h na to, itong x na to, these are called quantum gates, di ba? Now, itong quantum particle natin, or yung qubit natin, is governed by what is known as the Schrodinger equation. So, ibig sabihin, the Schrodinger equation is the one which evolves your qubit. For example, ito, tingnan nyo to, no? The Schrodinger equation is the one that describes the evolution of your qubit from 0 to 1 kapag nilagyan mo ng gate na x. No, kapag in-applyan mo siya ng gate na x, ito yung magiging 1 siya, pero yung x gate is actually it's actually the Schrodinger equation that describes the evolution of your qubit, no? Qubit state. Ganito din, no, sa Hadamard, no? Hadamard, you apply it to the state 0. Tapos, nagiging ganito yung state mo. So, paano nangyari yan? How did it go from 0 up to a superposition of 0 and 1, no? What is the loss of motion or loss of quantum mechanical law that evolves it from 0 to superposition of 0 and 1? It's called the Schrodinger equation, which is ito na. So the Schrodinger equation is a first order deterministic partial differential equation. Okay, that involves the instantaneous state of a quantum system. So itong Schrodinger equation makes use of what is known as the Hamiltonian. So yung evolution ng quantum mechanical system mo has something to do with the energy of that system. And the energy of that system is described by the Hamiltonian. No? You might have, di ba yung total energy, if you remember your physics, is just equal to the potential energy plus the kinetic energy. So, yung Hamiltonian na yan, that's the, yan yun siya, no? Now, since Schrodinger equation is linear, ibig sabihin, yung solution niya, it can have multiple solutions, di ba? Pag yung mga differential equation na linear, they can have multiple solutions. Now, if you do a superposition of all these solutions, or what you call this, summation, if you sum them, and the resulting sum is also a solution. Kaya siya linear, no? So, and also it's deterministic, no? Deterministic siya, which means that its instantaneous state at any moment. You can predict its future and past states. certainty. As long as you don't observe it. Yan yung ano doon, no? Catch. At ito yung itsura ng Schrodinger equation. Now, how do you solve that equation? Huh? Well, you assume a solution. Huh? So, you assume ano ba yung function na when you differentiate that function, it gives itself plus some multiplied by some constant, probably. No? So that function is the famous exponential. No? So if you get the derivative of an exponential, it will still give you an exponential. No? So kaya you assume a solution of exponential, and then you plug it into your Schrodinger equation and get the constants to get the answer, not to get this. That's the solution. Okay, so this says that if you know the initial state of the system at time 0, then you can determine its state at later time t by acting on the initial state with this operator. Okay. Now, what's so special about this? So what's special about this is this ut is actually a matrix. No? It's actually a matrix of the exponential of this. So, meron kang Hamiltonian mo, okay, which is also a matrix. You get the exponential of that to get u of t. Now, ano tong u of t mo? These are already your quantum gates, no? These are your x, these are your Hadamards, no? So that's how Hamiltonian is related to your quantum gate. Okay. So ito yung itsura ng exponential, no? So the exponential of a matrix A can be expressed as a power series, no? Or a Taylor series. So later, meron tayong exercise for you to verify something, no? by using this exponential of a matrix. Okay. Now, ito kasing Hamiltonian natin is is a special kind of operator, no? Kasi Hamiltonian is the energy of the system, di ba? So ibig sabihin, when you measure the energy of the system, you will always, if you measure the energy of a system that is represented by the state psi, then you will get a number. And that number is called the eigenvalue. And that eigenvalue is a real number. No? Hindi siya complex, no? Wala siyang imaginary part. It's a real number. So, how do we show that, no? So, let's start by defining what is a self-adjoint operator. Self-adjoint operator, pag meron kang operator A in its matrix representation, now A is acting on Y. Okay? So A is acting on Y. Now, if it is self-adjoint, then it is equal to the complex conjugate of A acting on the X, acting on the X vector. So that's the definition. So ibig sabihin, the complex conjugate of A is equal to A itself. No? So that's called self-adjoint. If you get the complex conjugate, it will just be itself, no? So very special. And why is it special, no? So, first and foremost, it's symmetrical, no? Kapag kinuha mo yung matrix niya, then if you do a so makikita mong mga entries sa upper diagonal are the same as the entries in the lower diagonal. Kaya siya symmetric. And what is so also special about this, no? Ito palang Hermitian is a self-adjoint. Pag sinabi mong self-adjoint, Hermitian yan. And Hermitian matrices are special, no? Kasi they have real eigenvalues. Okay? So, if you have a vector x, no? Or state x, and x is the eigenstate of your matrix A, no? So, ito yung ano, no? Ito yung definition ng this is the ng eigenvalue, eigenvector, no? Which is na-mention ko kanina, di ba? So, if we let X be the eigenstate of a Hermitian matrix A with a corresponding eigenstate, eigenvalue lambda, then we can show that the eigenvalue is actually real, no? So take a look at this. You start with this equation, no? So ang gagawin mo, ipapasok mo yan dito. Para mapasok mo yan, kailangan mong kunin yung complex conjugate ng lambda. Pero alam natin na this one is nothing but AX. Pero alam din natin na AX, na A is self-adjoint, which means pwede mo siyang ilagay dito. Kaya ganito na siya. Pero alam natin na this one here is just this one. So lambda X. Now, what do you see? You see that lambda star is equal to lambda. So anong klaseng number whose complex conjugate is equal to itself? No? That number is a real number. Kaya, itong mga Hermitian matrices na to, their eigenvalues are real. Oh, okay. Sandali lang, ha? Naubusan na ako ng I'm going to just plug in. Okay. So now alam na natin na itong mga operators, itong mga Hamiltonians that we use sa Schrödinger equation, these are Hermitian, no? And their eigenvalues are real. So example of this is the Hamiltonian nga. Hamiltonian is the energy of the system, no? So if you measure your eigenstate using the Hamiltonian, it will give you a eigenvalue, which is the total energy of the system. And that total energy is real. No? It has to be real. Okay. No, ngayon, tapos, ito pa. If the eigenvalues, if you have more than one eigenvalue, no? Just like in any quantum system, no? Maraming energy levels yan. Then, the eigenvectors corresponding to the eigenvalues are orthogonal to each other. Okay? So, sample. Ito, meron tayong lambda 1, no? And then this one here, which is the inner product. Kapag ipasok natin yung lambda 1 dito, you will get this one. Now, since self-adjoint siya, yung A, pwede mong ilagay sa kabila. Now, pero AX2 is, since X2 is an eigenstate of A, then it must have a eigenvalue, lambda 2. Okay? Now, tingnan nyo. Since X1, X2 are the same, then in order for them to be equal, then lambda 1, and because lambda 1 and lambda 2 are not equal, then it means that the inner product of X1 and X2 is 0. So ano ibig sabihin yan? They're orthogonal to each other, no? So if you remember your IJK, no? In vectors, no? The I dot J is equal to 0, no? So they are mutually perpendicular to each other. So ganito din, no? So any eigenvalue, any eigenstate that is from a different eigenvalue is orthogonal to the eigenstates, other eigenstates. Okay. Now dito na tayo sa spectral representation. Now any Hermitian matrix can be represented by this one here. It can be so yung matrix mo, it can be represented as a linear combination of your of this projection operators. Okay, so ito yung projection operators. If you remember, we discussed this earlier, no? Projection operators. So it's a linear combination of the projection operators weighted, no? Weight, ibig sabihin, weights pa. Weighted by the, or multiplied by the eigenvalue corresponding to that eigenstate, no? Of the projection operator. Okay. So you can decompose your operator like this. Okay. Now, it's a very easy exercise, no? You can just show that if you take the square of your projection operator, it is just equal to itself. Okay. Okay, now let A be an eigenvector. Let A be a an operator, and then this operator has a eigenvector x, which corresponds to the eigenvalue. No? You can see the pattern. No? Then x, the eigenvector x, is also an eigenvector of the matrix of the exponential. This one here, no? E raised to the ta. So how do you show that, no? So to show that, you just expand e to the ta into its Taylor series, no? Remembering that A is matrix, no? Mga matrices yan, no? So if you distribute your x into each of these, and then let it operate, no? So makukuha mo itong mga to, no? For example, ax will give you lambda x. A squared x will give you lambda squared x. And a cubed x will give you lambda cube x. Okay, and then you factor out your x, then you will see this. But this is nothing but the exponential of lambda t. Okay, so ibig sabihin, this eigenstate is also an eigenstate of the exponential of the matrix with eigenvalue e raised to the lambda t. Okay, no? So now suppose you have a operator and Hermitian operator, and then it is expressed like this. So Ano ba yung difference niya is meron siyang I, no? Meron siyang I in each of the, meron siyang imaginary number I as a factor in each of the terms, no? So therefore, e to the a, which is just equal to this, is equal to this one here, no? E to the lambda. So ibig sabihin, itong mga projection operators na to, napunta na sa baba, no? Napunta na siya sa baba. And then you can actually show that, no? That this one is correct, no? Okay. So the function exponential IA with a self-adjoint is also unitary, no? So, ibig sabihin, kapag unitary kasi, ibig sabihin, if you take the complex conjugate, then the complex conjugate is the inverse of that operator, no? So exponential e to the IA is equal to this, di ba? From the previous page, no? From the previous page, ito yung you can express e to the IA as the summation, no? The projection operators multiplied by the eigenvalue. Now, to show that exponential IA is unitary, then you just need to get the inverse of e to the IA. To get the inverse of e to the IA, you just multiply everything by minus 1. No? May negative 1 na dyan. No? But this is nothing but the complex conjugate of e to the IA. So ibig sabihin, these are equal. So which means this one is unitary matrix. Now this representation is yun nga, yung sinabi ko kanina, the gates are nothing but itong mga gates natin na ina-apply natin sa ating mga quantum state. They are governed by the Hamiltonian. And the Hamiltonian is the one being used in the Schrödinger equation. So ibig sabihin, kapag meron kang quantum gate, merong Hamiltonian yan. Ang tanong, ano yung Hamiltonian na yun? No? Can you compute for that Hamiltonian? Meron akong quantum gate. Can I compute for the Hamiltonian? Can I compute for the what you call this? The total energy of the system, which is the Hamiltonian? Yes. Suppose yung quantum gate mo is the Hadamard. What is the corresponding Hamiltonian of the Hadamard? No? So, kanina meron tayong ganito, di ba? Hadamard acting on 0 will give you 0 plus 1 over square root of 2. Tapos Hadamard acting on 1 will give you 0 minus 1 over square root of 2. Ito yung palagi nating nakikita in quantum computing. Pero what's the physics behind? Ano yung hindi natin nakikita dyan? Ang hindi natin nakikita dyan is yung Hamiltonian na ginagamit. Ano yung Hamiltonian na yun? Corresponding to your Hadamard. So, there is a way to compute for the Hamiltonian. No? Kasi, una, kukunin mo yung eigenvalue and eigenvector of the Hadamard. No? So, pag kinompute mo yan, kasi dalawa lang naman yung eigenvalues niya eh. it's either -1 or 1, no? So if you remember the eigenvalue equation, no? Uh, so meron kang h, no? So minus lambda I is equal to 0. That's the eigenvalue equation, no? So if you solve that, kasi mga matrix naman mga to, this one is identity matrix, and this one is your eigenvalue, then you will find that the eigenvalue is -1 and 1. Now, what are the corresponding eigenvectors of those eigenvalues? Now, if you compute, then you will get this. Okay? Compute. Okay? Now that you have the eigenvectors of your, now that you have the eigenvectors and the eigenvalue, so yung dalawa, you've got the eigenvector and you get the eigenvalue of your Hadamard, then you can now compute for the Hamiltonian. Alam naman natin kanina na yung Hamiltonian is nothing but can be written as the so can be written as the what you call this, the linear combination of this one here, no? So kung makita nyo, this one is the projection operator, di ba? These are the eigenvectors and this one are the eigenvalues. So if you do a linear combination, then you can write your Hamiltonian as this one here. Okay. So in other words, ito yung magiging actually this one exercise now show that x1 and x2 are like this. No, ito yung form niya. And then so what happens, no? So we can now represent h as e to the I, h for h, the Hamiltonian. So ito yung ano niya, no? So ito yung magiging itsura niya. Okay? With a corresponding Hamiltonian na ito. Okay? Okay, so this one is the this one is the linear combination. Okay, x1, x2. But we know that e to the I0 is e to the I0 is 1, di ba? So yun. Ito na lang natira. Tapos ito naman e to the I5, na? Okay, e to the I5. So ibig sabihin, yung Hamiltonian natin is, kasi ito 0 to, ito pi, na? So this is pi, this is 0. So kaya dito siya. So that's your Hamiltonian. So kapag you are doing Hadamard of 0 or Hadamard of 1, no? There is, so alam natin yan ano magiging result niyan, di ba? So Hadamard of 0, Hadamard 1. But hindi visible sa inyo o hindi visible sa atin na meron palang corresponding Hamiltonian yan, no? Which is ito yung ating kinompute. Okay, so that's the physics of yeah, that's the physics of the gates now. So actually, marami pa tayong ano, pero the thing is itong mga gates natin, they are may mga iba-ibang klaseng gates na. So alam natin na alam na natin to. This one is the X naught. Okay? Ito, alam na natin to. This one is a Z gate, no? these are actually called the Pauli matrices, no? Not sure if na-mention na yan, pero Pauli matrices yan, no? So not gate, no? Ito yung X na to. Tapos Z. No? So, kapag Z, in-apply mo sa 0, it will give you identity. Pero pag in-apply mo sa 1, it will give you a phase shift, no? By 180 degrees, no? Kaya negative 1 yan dyan, no? Negative 1. About phase, no? Kapag meron kang vector that's pointing in the X direction, and then suddenly it points in the negative X direction, ano ibig sabihin yan? You rotated it by 180 degrees, no? Kaya meron siyang negative 1, kaya na negative 1 na siya, no? Nakapunta na sa kabilang, nag 180 degree turn siya. Okay. Tapusin na lang natin 'to, malapit na. Now, ito yung mga basic gates, no? Na meron din mga tinatawag na rotation gates. So, rotate to the, ito mga rotation gates na to, this allows you to rotate along a certain axis. No? Ito yung mga axis na to, ito yung X, Y, Z. Okay? So, ito sila, no? Ito mga rotation gates na yan, it turns out na if you do the exponential of X, exponential of Y, exponential of Z, or Z, itong mga exponential na to will give you a matrix or a gate that will rotate your qubit along the axis kung saan siya naka-indicate dito. Okay? So for example, RZ. If you apply the operator RZ on the qubit, it will rotate it along the Z axis. Okay? Now, ang tanong, paano natin nakuha to? No, it looks very pag titingnan mo, it looks very complex, no? Pero since we are I mean sa mathematics kasi you can just derive things, di ba? Hindi mo maintindihan, derive mo na lang. So, how do we derive this? Okay? So, ito yung example, no? Let's have an example yung exponential of x, no? By the way, ito yung x naught na to, no? Ito yung x, this is the NOT gate. The exponential of a NOT gate is nothing but the rotation around the x-axis, which is equal to this matrix, no? Now, paano mo i-derive yung matrix na yan? Well, it's a exercise, no? Pero may hint. First, you what you call this, decompose it into its Taylor series, no? Plus, you can make use of these two Taylor series, no? Ibig sabihin, pag dinicompose mo siya into its Taylor series, and knowing the fact that x squared is equal to the identity, then you will see that e to the x is nothing but that you can decompose it into x sine x and cosine x. Siyempre, isa dyan may negative I, no? And then you can derive that, you can derive this matrix. So that's left as an exercise, no? But I'm gonna give you the answer, no? In a, ano na lang siguro, in a separate document. If you are curious. So, okay, ganito nga yung kanyang ganito yung kanyang matrix. Bakit ko masabi na rotation yan, no? No? How can you say it's rotation? Okay. Kung titingnan natin, sino ba yung pinakasimple dito? Ito. Okay? So, yan yung siyang pinakasimple. So, let's try that, no? Let's try that. Let us show that RZ of A is a rotation along is a rotation around the z-axis. Okay? So, okay, to show that it's a rotation, ito, wala na tayong choice kundi to use matrix multiplication. No? So, ang operator natin, we we represent it as a matrix and then multiply it by the what you call this? By the general state of a qubit, no? The form of the general state of a qubit. So, ito siya. So, cosine theta na yan, at ito the i sine theta. Okay? So, ito yan siya. Now, itong RZ na to, ito yung matrix niya, di ba? Now, so if you multiply that, ito yung magiging itsura, no? Okay? So, e to the I alpha multiplied by cosine theta, tapos 0 kasi ito eh. So, ito lang yung matitira. Tapos ito din naman, e to the I alpha over 2 multiplied by this. Nandito siya, no? Okay. Tapos ito, you can write it, you can expand it back, no, into its vector form. So, ito na itsura niya. Okay? Now, tingnan natin. Kasi alam natin na any state, any quantum state will stay the same even if you multiply it by a global phase factor. Then we multiply it by a global phase factor, no? to make our calculation easy. So, anong global phase factor ang ating i-multiply, no? Siyempre, we want to eliminate this. Kaya, ito yung i-multiply natin. Okay? So, if you multiply it, ang mangyayari is ito, naging 1. Okay? So, nawala siya. Tapos, ito, ang nangyari is, ito yung, yung e to the I phi na yan. So, napunta na siya dito, no? So, by the way, ito, what happened to this one here? So, naging e to the I alpha. So, naging itong dalawa, pag minultiply mo, naging e to the I alpha na lang, di ba? Kasi e to the I alpha over 2 plus e to the I alpha over 2 is equal to the e to the I alpha. So, kaya, naging ganito siya. Okay? Now, kung titingnan nyo, anong difference nito at nito? So, ang difference lang is that itong yung theta na yan, napalitan ng theta plus alpha. Okay? So, anong ibig sabihin yan? By applying the gate RZ alpha, your qubit is yung kanyang angle na theta, phi, nadagdagan ng alpha. Okay? So, nadagdagan ng alpha yung phi. So, ibig sabihin, nag-rotate siya. Saan ba yung phi banda? Okay? Saan ba yung phi banda? Sorry. If you take a look at this one here, the black sphere, no? Wala yung black sphere ko. Balikan lang natin, no? So, ibig sabihin, ito yung phi eh. Okay? Ito. Sorry. Okay. Ito. Ito yung phi, no? So, nadagdagan siya ng alpha. So, ibig sabihin, nag-rotate pa siya papunta dito. So, since ito yung z-axis natin, nag-rotate siya around the z-axis. No? So, that's what happened when we multiplied it by, when we applied this operator. No? So we have just shown that this operator is a rotation around the z-axis. And you can also show the rest of the operators kanina, no, na Rx and Ry. Okay? They are correspondingly rotations around the x and y axis. Okay. So finally, before we go, let's I will show you, no, if you do that, yung Java, itong block sphere, no. So let me just unshare my screen first and share in the other screen, no. Let me unshare, stop share, and then I will share in the other screen. Saan ba yan? Share in the other screen. Okay. So, ito siya, no? Now, let me just do this now. So ito yung block sphere, no? So ito yung qubit mo, and ito yung block sphere na to. So kung titingnan nyo, the block sphere is the set of all possible states of your, the set of all your possible states of your qubit. Now there's another term for that, no? The set of all possible states of your qubit. The term for that is the Hilbert space. Yeah, ito yung Hilbert space mo, no? So let's take a look, no? Suppose I'm going to rotate around the y-axis. Yan. Okay? Rotate, or ito yung y natin, di ba? So rotate around the y-axis. Oh, sorry. X pala yung inano ko. Rotate around the y-axis. Yan, ha? Okay. Balik natin. Okay. Now, I want this to rotate around the z-axis, no? Papunta dito. Ito yung z. How do I do that? This one. Okay? Okay, balik. Tapos, balik natin, no? Now, let's do a Hadamard, no? Yeah, Hadamard. Now, let's rotate this around the z-axis, no? RZ. Ito yung dinerive natin kanina, no? Ayan, no? So, klaro-klaro that it rotates around the z-axis. Tapos ito pala yung general qubit state, no? So, ganun siya. Tapos, balik natin. Paano ito ibalik? Hadamard ulit natin. Okay, so actually hanggang dyan lang ako. Sorry for I nag over ako sa time. Back to
Okay.
you.
Okay, Sir Bobby, thank you for that wonderful
Share
talk
ko.
on block spheres. Medyo I got confused lang. Kasi
Yeah,
it's like,
you can ask questions.
yeah, I got confused lang a bit. Pero like, a lot of it went over my head. Pero one thing I note is, it's yung other formulas, they're really similar to the formulas I've seen in rendering, in graphics programming ba? Kasi that's
Tama.
my
Tama ka.
interest.
Tama ka.
Particularly the rotation matrix
Oo.
has an equivalent matrix in graphics programming when you
Oo.
magro-rotate.
Tama.
Not sure
Oo.
if yung quaternions also apply, pero yeah, there are similarities talaga. As what I like, at the underneath talaga, like I noticed yung foundational topic for quantum computing and graphics programming talaga is linear algebra and a bit of trigo and geometry along there. That's what I
Yes.
noticed.
Oo. That's
So,
good.
So we have one question. So this participant asked, can we have book recommendation regarding this lecture or quantum computing itself for us to use for self-studying?
Okay. So there's actually a lot of books now. What I can recommend is marami mga books, no? But what I'm using right now are itong dalawang books na to, no? Let me just show you, no? Let me just show you. Probably I will turn on my video. Okay, you can see me. Yeah. Okay, hold on. So,
Yeah. Medyo nakikita naman.
I
Quantum,
will remove ano
screen share.
what you call this, background, no?
Ah,
If I blur my background, kita ba rin? Okay, kita na.
yeah, better, sir. Yeah, there. Quantum computation and quantum information. Hindi ko lang nababasa yung authors.
Sige, at tanggalin ko na lang yung ano ko, choose virtual background, none. Yeah.
Ayun. So, quantum computation and quantum information by Michael A. Nielsen and Isaac
Nilsson Chuang.
Chuang. Yeah,
Ah.
there.
Tapos, another one here is this one here. If you want the applications.
Explorations in Quantum Computing by Colin P. Williams. Yun.
So, yun. Then, magpadala pa ako ng ano, mga tawag nito, mga ibang references.
Mm.
Ayun.
Yeah. Those are really interesting sir, references. Pero I would probably add siguro, since sir, I noticed there is linear algebra. Maybe we could recommend Gilbert Strang as well for the linear algebra basics, at least for the basics or foundationals. Can we recommend that?
I haven't seen that, pero if you think that's yeah.
Yeah,
Hmm.
Gilbert Strang has one of the best books on linear algebra. That's why I'm recommending it.
But by the way, I just want to emphasize na yung
Yeah,
linear
yeah, yeah.
algebra dito sa quantum computing, now you will not be computing a lot of matrix operations dito, ha. It's more of the abstract linear algebra, no? You only go down to the what you call this, to the matrix operations kapag ano na, actually bihira ka lang gagawa ng matrix operations dito, eh, kasi usually we are going to do this as well, no? When I introduce you to the algorithm of Deutsche-Joshua, no, and Bernstein-Basirani, yung mathematics dito is more of a, di ba, kapag nag-matrix ka, is more of a summation yan, di ba? Summation formula. So, yeah, so ganun siya. So, as long as maintindihan mo yung mga concepts of closure, completeness, what you call this, linearity, no, and basis vectors. So you have an operator, and you have two sets of basis vectors. How do you convert from one basis vector to the other? Yan, ano na yan, okay na yan.
Di ba yun, sir? I'm not sure with the symbol. Those were eigenvalues, di ba? Yung
Oo, may
symbols kanina.
eigenvalue, ano din.
Yun.
Oo.
Yeah, that's still haven't completed eigenvalues. Ano pa kasi yung nabasa ko? I was reading Lingel.
Meron
Yes?
ding libro that is very useful that I used before. It's called Advanced Engineering Mathematics by Wiley Barrett. It's very nice as well.
Oh, okay. So at least those are what we could recommend to everyone here. Okay, so anyone added more questions for Sir Bobby?
Yeah, UK Thomas Wong also. It's supposed to be for high school students, so you can also use that.
Okay. Right. So seems like no more additional questions, Sir Bobby.
Oo nga eh, sorry, yun nga eh, nag-ano tayo. There's another one speaker sana, si, si Carl.
So ano man, sir?
Yeah, next week na lang siguro yan.
Next week si Carl.
Hmm.
Sige. So, I guess we can move na to the closing.
Oh, thank you,
Is it-
Carl. Yeah, closing. Meron pa pala yung, ano,
Sir, last question. Title po ng Dirac book.
oh, yeah. It's called The Principles of Quantum Mechanics.
No.
Oh, you can download it from the internet. Libre na yun kasi sobrang luma na eh.
Okay.
But it's one of the best books in quantum mechanics talaga.
Ayun.
Kasi he
So,
derived everything from scratch eh. Even the operators, no? Di ba the mathematicians usually begin with definition, di ba? Eh yung sa kanya iba siya eh. He's a physicist. He just derived everything. So kaya maganda siya.
sir, ano yun, sir? Principles of quantum mechanics. Ayun. Okay, sent it na in the message.
Yeah, PAM Dirac. So Paul Adrian Maurice Dirac.
Right. It's nice. So further questions, anyone? Honestly, that was a really heavy topic. Like,
Oh, pero I'm going to give you the slides so that you will, it's very essential talaga na you know this, at this level, yung quantum computing para ma-appreciate nyo siya. Hmm.
right.
Pero
So
wala pa nga computing dun eh. That was still quantum mechanics. No?
Mechanics.
Ang computing next week.
Next week pa, sir?
Ah.
Okay. Okay. Right. So, anyone have more questions? Seems like wala na. No more questions. Anyone? I guess we can move na
Oh,
to
yeah.
the next
Ano ba yung
slide.
next?
Yung photo op na lang siguro.
Okay,
Kasi
photo op.
matatapos naman.
Yan, temperature check. Oh, hindi na. Photo op na lang.
Photo op matatapos naman, tapos may announcement naman tayo next.
Yan, sige, photo op.
Okay, guys, so let's do a photo op. We're almost gonna end. We're just going, please don't leave after the photo op muna. Kasi we'll have a bit of a announcement. A few students here would want to find out the announcement. So thank you guys again for joining us in this today's lecture series on QNLP. Before you go, we have an announcement. See you, sir, next po. So we have invitation letters of the hackathon here in Tacloban coming this October 18. And those letters have already been sent to your schools, at least those qualified. So the first school that has qualified, one of the first schools is UP Tacloban College. So there will be 2 teams from UP Tacloban. Next up is from VSU. Shout out to UP Tacloban and VSU over there. So 2 teams as well, and AMA Tacloban, 2 teams. Then followed by BIPSU with 1 team, and then SLSU with another 1 team. And this next one is Philippine Science High School Eastern Visayas Campus. There's 1 team. And lastly, the INCS, so Isabel National Comprehensive School. So they have 1 team. So these are all the schools that will be competing for the Quantum Computing Hackathon this October 18 here in Tacloban, particularly in UP Tacloban. So, any final questions, guys? Panhabol lang. If ever, Yeah, EMA. Di ba ACLC ba? Or let me just be clear. ACLC is different, di ba? Or are they the same? I am not sure. It's different. Okay. Okay, so shout out to all of these schools. Sino po yung ano? Anyone for yeah, a lot of people here are from UP, VSU, MA. Anyone from SLSU? Somewhere, anyone there? Meron ba? Nice. Tapos Pisay siguro? I've only seen the 4 schools, no. Yes, go Pisay, batch 2015. I'm that old. Tapos INCS, do we have anyone from INCS? Anyone? Kahit magpaano lang, pagalaw ng baso. Okay, so siguro like outside or anything. So yun lang guys. So those are the announcements we have for the Quantum Computing Hackathon. And good luck. See you on October 18. So sige sir, next slide na. So yun guys. So this is the code for yung attendance. So I guess that's it for now. So share. Ayan, okay. So thank you everyone for joining us for today's hackathon lecture series. And we hope you learned a lot. And siguro you eventually know you have learned more about quantum computing. So thank you everyone. See you again next time.
Thank you, everyone.